Hi, welcome to another edition of Ordinary Differential Equations. We are going to continue our discussion about Laplace Transform. So let's go ahead and get started. So remember last time we mentioned that Laplace Transform is a method that is applicable to certain differential equations. It's of significant use in engineering in a variety of areas. So we are practicing the concept and the application to ODEs. Let's mention again what the formula was. So we said if you have a function f of t, Laplace transform of it is obtained by multiplying by a function we call a kernel, which is a function of two variables s and t, and followed by integration from 0 to infinity. Integration is with respect to the variable t. The function has to die out at infinity at a certain rate for this integral to be valid. The result of it, we write it with two notations. One is to use the capital letter that we have used here for the original function here. Alternatively, we can use the script L notation, L for Laplace, and we are applying that transformer to f to get our result. So we started last time with certain basic functions. We said we start with the pet functions and see what is the Laplace transform of them. This is a table that I recommended that you try to write over and over again so that you become familiar with the entries of it. We have our original function listed here. The Laplace transform of it is here, and we said we always have some sort of a restriction on what kind of s is legitimate so that the integral becomes a finite value. So if you remember, we started with basic function 1, constant function 1. The Laplace transform was 1 over s. The restriction was that s has to be positive. Then we looked at the exponential, and we said the Laplace transform of it is 1 over s minus a, and s had to be larger than a. Then the next easy one was cosine and sine hyperbolic. They call it sometimes cosh. So for this one, we had the s over s squared minus b squared. S had to be larger than absolute value of b. For sine hyperbolic bt, we had b over s squared minus b squared, and same restriction. We listed some other functions without proof. Today we are going to add the proof for them and extend this table so that it becomes a much longer table. At the same time that we are making this table, we are going to have a table for general functions. So here is a secondary table. We have a long list of entries here as well. The very first entry will be just a definition itself. Of course, if you have the function f, its Laplace transform is capital F, which is defined by this formula. We introduced you to linearity, which meant if I have two functions f and g, and I know their Laplace transform, and I multiply them by some numbers and add or subtract, the same thing is going to happen to the Laplace transform. So here we have AF plus BG. And we also said this is the only simple rule of this type we have. Just like in integration and differentiation, they warn you that the multiplication here does not turn into multiplication here, or a division to a division here, and so on. We have the same warning here. That is, we don't have, there are certain rules that look very appealing, but they're just not correct. If you have a product of two functions, the Laplace transform of that product is not going to be product of the Laplace transforms. So this is, we have to draw a cross on that. F over G also, the Laplace transform of it does not turn out to be ratio of the Laplace transform. Or for f squared, the Laplace transform of it is not going to be f squared. So these kind of elementary mistakes have to be avoided. So we might as well just go ahead and erase them. Essentially, we don't have really any simple rule other than this linearity. Okay, one of the nice simple rules that we can add here is for f, a function whose Laplace transform we know, times one of our pet functions. The simplest of these things is just the exponential. If I have a function and I multiply it by an exponential like this, then the Laplace transform of this product can be found very easily. If this is f of s, all that happens here is that the Laplace transform gets shifted by a. So the answer becomes f of s minus a. So this is one of the first rules we want to investigate, see how do we actually make use of it, and also where does the formula itself come from. First, let's make sure we understand what's the meaning of it. So on this side, I had a function f of t multiplied by exponential of at, and what happens is that the Laplace transform of f that I had before, the s of it gets to be replaced by s minus a. So what does that mean? So suppose I want to calculate Laplace transform of exponential of 2t times cosine of, say, 3t. The kind of expression we have come across quite often, because these are all pet functions. So how do we go about doing this thing? First, we remind ourselves what was the Laplace transform of cosine of 3t. Well, for that we had the formula last time. I have to still prove it here for you, but let me include it here so that we have a reference. So cosine, regular trigonometric cosine of bt, Laplace transform was s over s squared plus b squared, the restriction being s just larger than 0. Similarly, for sine of bt, formula very similar to this one, except that the sign in denominator is plus. So first we go ahead and pick up our formula here, which is s over s squared plus 3 squared. Then the question is, well, what is 2 gonna do? According to this formula, 2 is gonna replace occurrence of every s with s minus 2. So when you multiply by exponential of, say, at, your s's get to be replaced by s minus a. So here, s that shows up here, this s, has to be replaced by, let's write it, instead of s, I write s minus, s minus, my a is 2. Same way in denominator, this is s minus 2 squared plus 3 squared. So these s's got replaced by s minus 2. That's the meaning of this formula. It's very simple to prove. Let's go ahead and prove it. So as a example of these general rules that we have here, let's see where do these rules come from. So suppose I want to calculate Laplace transform of exponential of at f of t. I strongly recommend those of you who are headed toward the theoretical side of engineering, more design aspects, and also perhaps having an eye toward going to graduate school and such, try to come up with this proof yourself. Okay, and first time that you come across this thing, it could take quite a few minutes. God knows, maybe it takes a whole day. But as you get the hang of what's involved here, then you are going to speed up, and the next problem is going to take substantially less time, and you essentially find your groove in, so to speak, in that area. Let's go back and see what happens. So at any place here, feel free to stop and try to continue yourself. So Laplace transform is the kernel times whatever you start with, which is now in this case exponential of at f of t dt. So this is step 1. What do you think I'm going to do in the next step? Again, I cannot emphasize enough. Pause and try to figure out for yourself. Well, makes sense to combine these two. So I have exponential of, let's factor s minus a t So I just combine these two by the rule that we said, b to power of m times b to power of n is b to power of m plus n. This is just that rule. Now what? Now, as simple as this step is, it's a sign of having stepped up your mathematical understanding. The issue is the following. If you have a parameter here, in this case s, that now is the argument of this function, if you replace this thing by anything, that one also is going to replace same way. So whatever is here is the argument of that function out there. So what is it that I have now? I have replaced that green stuff with this green stuff, which is s minus a. So if previously, if I had f of s as a result of this integral, what happens here now is f of s minus a. That's all. You have to try to understand really what that means, other than just mechanically replacing something with something else. That constitutes the proof of that formula. So if I have a function whose Laplace transform I know, and I'm multiplying by an exponential, all I have to do is replace s by s minus this multiple. There was another formula we had last time, which we said without proof. Let me include that here also. So you remember we had t to power of n, that was n factorial over s to power of n plus 1, s being positive. Now you can say that if I have exponential of at times t to power of n, what happens here, I'll have n factorial, and I'll have s minus a to power of n plus 1. And previously s had to be positive, now s minus a has to be positive, which means s has to be larger than a. While we are at it, let me write the similar formulas for these two, because we see them quite often, so we might as well allocate some space for it in our table. So what happens is that, okay, let me see if I can encourage you to write the right hand side of this thing. What should I write on the right hand side? Essentially, you have to come up with the answer in a second. So simply a substitution, s minus a over s minus a squared plus b squared. Same with the sign, exponential of at sine of bt. There's no substitution to do in the numerator because there's no s there. S minus a squared plus b squared, and these have same restrictions. S now is larger than a. What about restriction in these problems? Well, the most strict of restrictions that you have for f and g is going to apply here. Like if for f s had to be larger than 5 and for g had to be larger than 10, then for this we go for the more strict of the two, so s had to be larger than 10. Here if s had to be larger than a certain number, now s minus a has to be larger than that number, and so on. Okay, now off to the next of our discoveries. One more rule we have here. So here I have, of the pet functions, I have taken the exponential multiplied by any function, and I have a simple formula for it. It turns out same thing happens for a similar thing happens for a polynomial. Similar meaning we have a simple recipe here. For the polynomial is going to be a little bit more complicated than that. The way it goes is that if I have a function whose Laplace transform I know is f, if I take it multiply, here's the simplest polynomial t. What it does to the function is quite unexpected in this case. It actually differentiates our transform. That is, I have to take f and differentiate it with respect to s. So I can write it f prime. And also it multiplies it with a minus. Okay, so if I have a function, I take multiplied by simplest polynomial, just a t. What it does is that it differentiates this thing and multiplies it by a minus. While we are at it, let's list a few others. If I take t squared and multiply by a function, essentially like t multiplied by this one, it differentiates one more time, multiplies by another minus signs, which at the end turns out to be plus now, and now it becomes f double prime of s. Let me see if you can guess what happens if I take t cubed and multiply by f of t. What do you think is going to happen on the right hand side? Yes, this is going to flip, and now you have to take triple derivative. So if you want to insist on general rule, although we are not going to use it all that much, if you have power n being a whole number, this will be minus 1 raised to power of n, and now we want to indicate n differentiation. Well, it's going to look pretty ugly if I keep putting tick marks on top of my function. I want to indicate n, but people are going to get confused with this, thinking that it's a power. So in mathematics, to avoid that confusion, we put this thing in a parentheses or some notation like that to indicate that is how many times you're supposed to differentiate, not that you're raising to a power. It is how many times you differentiate. So let me maybe make room here. So if we go ahead and establish the first one, then all the others are going to be established based on the very first, and that's also going to be in some sense straightforward, but in some sense it requires advanced calculus. There is a subtle point to it that is actually advanced topic, but we are going to treat it at our level. So let's go ahead and see what happens. Laplace transform of a t times f of t. Well, what is that supposed to be? Well, as usual, 0 to infinity. My kernel times the original function t f of t dt integrate it from 0 to infinity. Now I notice that this expression can be written as derivative with respect to s. So to clarify, I'm differentiating with respect to s, not with respect to t, of exponential of minus st. If I differentiate this thing with respect to s, a factor of minus t comes in front, so actually I need a minus as well. So this is same as that, times f of t. So far so good. That's rather obvious. Next step is not so trivial. We are carrying out two operations. One is this integration and the other one is this differentiation with respect to s. For most cases, these two can be interchanged. That is, you can integrate first and differentiate later. So I can take this thing outside. Sorry. Well, two things. First, this is just our Laplace transform. That's f of s. Second, this differentiation, there's no confusion as to with respect to what. When you do this integral, there's no more t left for you to be worried that am I differentiating with respect to s or with respect to t. Here, yes, there is a confusion, but here there isn't. So I don't need to use partial. I can just use the ordinary. And that is just a Laplace transform. Simply, you can write it as minus, and that derivative you can write it as a prime, and then we are done. Okay, so there is a very significant issue here that typically comes up in a course like advanced calculus or real analysis or something like that. It's beyond the scope of our class, and for the functions that we are investigating, the operation is legitimate. So that takes care of the proof of this. But it might look like mysterious, or what is really happening here. So to understand what is involved, let's ask what is the Laplace transform of, say, t times sine of, say, 3t. Before we actually carry this thing out, do you remember why is this thing significant? Where was it that it showed up? What context was it that we had t times sine of t? Can you think about that for a second? Where was it that we saw this type of an expression? Well, if you said resonance, you have been paying attention. When you have resonance, this kind of things do show up. So this is relevant really to us, that we need to know Laplace transform of this. So the question is, how do we do that? The answer is, you start with that expression without t. Well, what was that? Sine. Here's sine. Of course, by now you better know it by heart. So this is 3 over sine of, s squared plus 3 squared. Let me just write it as 9 for now. So what does this formula says? This formula says you have to differentiate this. It's just an s. You have to differentiate with respect to s and flip the sign of it. So what we have to do is minus 3 over s squared plus 9, the whole thing prime. So let's go ahead and carry this thing out. Let me make room. So I'll differentiate derivative of numerator 0 times denominator minus derivative of denominator, which is 2s times numerator So we have to apply, remember, if you have quotient rule, numerator over denominator, numerator prime, denominator minus numerator times denominator prime over denominator squared. So that was the recipe there for differentiation. So now I have s squared plus 9 squared. To simplify, let's write it like this. So I have 2s and 3 times 3, and then I have s squared plus, remember what 9 was 3 squared, then squared. So you can create formulas like that for yourself and put it in your table and such. You can also, let me just ask you to do the following. What is, you'll have several questions like that in your homework. What's Laplace transform of t times, say, cosine hyperbolic of 6t? And if you want to be more ambitious, say t squared times, let's just say cosine of 7t. So now I have t squared, that means two derivatives. So you have your job made for you, that you have to actually carefully differentiate and such. Once you do that, you want perhaps add the general formula to your table so that you can do that quickly. What other problems do you want to investigate? One of them is the formula for t to the n. So t to the n, we can investigate two ways. Question the following: what is the Laplace transform of t to the n? So that's, we just claimed, but we didn't really show it, that this is the following. So the question is, well, how do you show that? Where does that formula come from? We have several ways of approaching this thing. One of them is based on the formula that we just established. You have to take the Laplace transform of 1 and differentiate it so many times. That's one style. Another style is to approach the problem from just definition. So for suppose I want to calculate Laplace transform t to the n. From the definition, it's supposed to be this integral. So I just write it, t to the n exponential of minus st dt. Then what? Well, as usual, standard procedure in many of these problems is to do integration by parts. Let me just remind you, if you have u times the derivative of another function, then the integral of that is u times v minus integral of this expression with the roles reversed. Integration by parts is just a sister rule of product rule, so it's really same thing. So what we have here is u is t to the n, dv is exponential of minus st dt, and then du becomes nt n minus 1, and v, antiderivative of this, becomes exponential of minus t st over minus s. So those are the ingredients we start with, and then we can carry this thing out. So u times v becomes t to the n exponential of minus st over minus s minus v du, product of these two. So v is exponential of minus st over minus s times du, which is n t to power of n minus 1, then dt. Now we have to do two things. This limit that we have to enforce it here as well, and enforce it here as well. And then we have to clean up. So let's go ahead and do that. So step 1, This is minus t to power of n exponential of minus st over minus s. This minus and minus makes a plus. This n and s gives me n over s. And then I have exponential of minus st t to power of n minus 1 dt. Except that I have to have these integral limits. A formula like this, going from power n to power n minus 1, in calculus you refer to it as a reduction formula. You're reducing the exponent. Our process is going to be simple and successful if the exponent that we have is a positive exponent. So we start this thing with n being positive, and of course we are taking whole numbers, so meaning n t is going to be 1, 2, 3 and so on. Well, here a positive exponent times an exponential at infinity is going to tend to 0, because exponential is going to drag this expression into 0. At time 0, this thing is also going to be 0, so this whole expression falls out, and then what we have is just n over s integral from 0 to infinity of exponential of minus st t to power of n minus 1 dt. Well, what we have here on the right hand side, this is Laplace transform of t to power of n minus 1. So let's rewrite what happened. So let's if n is any number like 1, 2, 3 and so on, then Laplace transform of t to power of n is n over s of Laplace transform of t to power of n minus 1. Let's apply this. What's the easiest application? Let's take n equal to 1. Laplace transform of t, this is 1, and this is t to power of 0, which is just 1. Laplace transform of 1, you remember, was 1 over s, so this becomes 1 over s squared. Let's try another one. Suppose I want the Laplace transform of t squared. This formula tells me that is 2 over s times Laplace transform of t. But Laplace transform of t, I just found it. So that is 2 over s times 1 over s squared. So it becomes 2 over s cubed. Now, as usual, I'm going to insist you do the next. Laplace transform of t cubed. Follow that process as opposed to just saying the formula out. I like to see the process, not necessarily so much the final answer. So go ahead, take a few seconds and do Laplace transform of t cubed. So of course it becomes 3 over s Laplace transform of t squared, which we know what it is, 3 over s times 2 over s cubed, so that becomes 6 over s to power of 4. So these numbers 1, 2, 6 and so on, that's one of the most famous sequences you see in calculus. What is that? What is the pattern? 1, 2, 6. What's the next number? Okay, so every time we are multiplying by the next number. So I had 2, I multiply by 3, next time I multiply by 4 and so on. So when you multiply 1 times 2 times 3 times 4 and so on, what are you creating? You're creating the n factorial. So in this case this is just 3 factorial over s to power of 4. And of course you can keep going. One of the most mathematically interesting aspect of the table that we are making now is this type of a formula that for n t to power of n, for t to the power of n, we have n factorial. Why is that interesting? Because mathematicians kept thinking about extending the factorial function to numbers that are not whole numbers. So for 1, 2, 3, 4, and so on, this is a trivial thing to decide what is n factorial. But suppose somebody wants to insist on factorial of 2.5, or 5 3/4, or factorial of pi and such. What is that number? So mathematicians actually debated the issue for about a century. Sometimes you complain that your homework's a little bit taking too much time, but imagine certain problems in mathematics extended for a very long time. So if I have t to the power of 2.5, what would I put here? That is that resulted in one of the major functions, new functions in mathematics. I hope you become curious enough to go ahead, try to dig into that. So this was one way of arriving at this formula. You can devise other methods for getting the same type of an answer. So what do we have so far? Let's go back and review. We have several of these pet functions and their products. There's one product we didn't write, which is like cosine times an arbitrary function, or sine times an arbitrary function. Result is can be written, but it's going to have complex numbers in here, and I just avoided that. One of the formulas that we did not explain was the formula for ordinary trig functions. How do we find these ones? Last time we just said, well, they look like these, but where does this plus come from? Well, this derivation, again, you have several choices for it. You can do integration by parts. There are some videos and write-outs in my website. You can read that. In your homework, you're asked to do this thing by using complex numbers. So that's method number 2. And method number 3, we can use one of our favorite styles of approaching this kind of problems in the course, which was method of undetermined coefficients. Actually applies here too. So let's go ahead and for the last item for today, ask the following question. What is the Laplace transform of cosine of bt? So what we are asking here is not what is the formula, explain the derivation. How do you get there? Okay, so the answer to this is not just s over s squared plus b squared. That's the final answer. But where does it come from? That's what the question is. So we said you have 3 methods to go after. One is complex numbers. Well, let me write better than that. Euler formula. So this shows up in your exercises. Euler formula says e to the I theta is cosine theta plus I sine theta. And then you can also write same thing for negative. So if you add them up, cosine theta becomes e to the I theta plus e to the minus I theta divided by 2. So a cosine can be written as an exponential, and we know what is the Laplace transform of the exponential. So we can just replace the items and add them up. The only bit of complication is that the nagging concern is how about these complex numbers and such. However, if you ignore that issue and just go through the process, you are going to find the same formula as we have found before, and that's what is shown up asked from you in your homework. So one method is to use Euler formula. Method 2 is our trusty integration by parts. So description of this thing I write out in my website, and you find lots of videos on that will do exact that problem. Method 3 to do this problem is method of undetermined coefficients. Since we have seen this thing before, let's go ahead and try see how does that help us get an integral. So as usual, this is exponential of minus st cosine of bt dt. Now that integral has to be evaluated from 0 to infinity, but before we do that, let's just go ahead and find the indefinite integral, and then we are going to do that job later on. So the question is, how do you actually carry out this integral? It's one of the standard questions in calculus 1 perhaps. So here we say, well, we have an exponential times a trig, and answer is going to be a mix of this trig and the other one, which is the sine. So what I expect the answer to be is exponential of minus st times some multiple, as yet I don't know what that's going to be, cosine of bt, but I suspect there's also going to be sine, so sine of bt. And then of course for indefinite integral there is a constant there. The question is, who's a and who's b? Well, very simple method for determining a and b as in a method of undetermined coefficient. What do you think I should do? So for the last exercise of the day, how would I approach this problem to figure out a and b? Hold this thing and spend maybe 5 minutes, see what would you think we should do. Well, if antiderivative of this thing is equal to that, it means the derivative of this is equal to that. So that's where we start with. Say exponential of minus st cosine of bt, therefore has to be the derivative with respect to t of st times a cosine of bt plus b sine of bt. Of course, derivative of c0 is a constant. So I turn the equation around. So if you differentiate this thing, you have to get that. So I'm going to go ahead and differentiate this, equate to that, set the coefficients. For cosine has to be 1 and for sine has to be 0. That's going to give me what a and b are supposed to be. So I avoided the integration, and now instead I have to put up with differentiation. Well, differentiation is easier. A derivative of the first one, so I apply product rule, minus s exponential of minus st times a cosine of bt plus b sine of bt, and then derivative of second times first, that is exponential of minus st times well, I have a factor of b here, so it's going to be b a sine of bt and another b here, so it's going to be b capital B cosine of bt. Well, the two sides are equal. What am I going to do? I'm going to collect my cosines and equate it to the cosine here, and sines, well, there's no sine here, so that's going to be 0. So let's go ahead and clean up. So I'll have exponential of minus st, let's put that outside. Then I'll collect all of my cosines in one basket and all of my sines in another basket, and there's an exponential multiplying everybody on the outside. Cosine, I have minus sa, and here I have plus bb, and for the sign in my basket there's going to be minus SB, and here I have minus BA. So minus SA plus BB has to match the coefficient here, which is 1, and minus SB minus BA has to match the coefficient for the sign on the other side, which is 0. So I just go ahead and write minus SA plus BB, that matches to 1, minus SB minus BA, for the sign it matches to 0. So for example, here you can say A is going to be equal to minus SB over B, which when we put here it becomes S squared over B times capital B plus little b times capital B equal to 1, which when you factor a b out of it becomes S squared over B plus B equals to 1. We clean up a bit B. There is this expression that we see quite often. So all of that gave us B is equal to little b over S squared plus B squared. And when I multiply this by minus S over B, this B cancels that B, and all that is left is a minus S in the numerator. So what that implies is that we have our integral. Let's go back and write our integral. I have the following: exponential of minus st cosine of bt a. I have the same denominator all over the place, so to clean up, let's write it just once. A, what was it? A cosine plus B sine the whole thing was, so A cosine plus B sine times exponential of minus st. And we have our constant of integration. So what we achieved here is one of these tricky integrals that shows up in calculus. Well, Laplace integral is from 0 to infinity. Forgot to put my differential. So what do I have to do? I have to put time 0 and time infinity. At infinity, this is going to drag everything down to 0 provided that s is positive. So at infinity I'm just going to have a 0. At 0, well, this exponential becomes 1. At time equal to 0, this is 1, this is 0, and I'm subtracting s times 1 over s squared plus b squared. And there was a minus here already. So when you subtract it, you get s squared over s squared plus b squared. So this was a roundabout way of calculating the Laplace transform of a cosine from scratch by using items from calculus 1. So again, in your homework you are going to be guided to do Euler formula, in the website you're going to find two styles at least of performing integration by parts, and now we did our undetermined coefficients. So quite a bit of work was involved to get us used to this table. By now our table is kind of extensive, but when you look at all of this thing, there is one big question. What does any of this have to do with differential equation? I don't see any differential equation here. These are okay, you have some nice functions, you take their Laplace transform, and there's some general rules here, but how does any of this apply to ordinary differential equation? Well, that all depends on a formula for a derivative. What is Laplace transform of a derivative? That is a make or break point for this approach. If for Laplace transform of a derivative we have something recognizable, easy to handle, that is going to make it applicable to ODEs. Yeah, let's leave that for the next presentation. Maybe you can try to work it out yourself. Start from the definition of Laplace transform, see if you can find out what would be the Laplace transform of prime. So that's going to be next level up, which is going to be the bridge to our solution of ODEs. Okay, until next meeting, good luck and God bless.